Oh, that's good.
Okay.
Whoa. Oh, that's very
Can we do the second
a
one
decent
now?
distance, but wow, that sprayed so much further. Crazy.
Say you have a beaker filled with water. At the surface of the water, there is a force as a result of atmospheric pressure, which is equal to the pressure times the area. By contrast, at the bottom of the beaker, there is still the force due to atmospheric pressure, but there is also a force from the weight of the water. Using the relationship that mass is equal to density times volume, the expression for force at the bottom of the beaker can be rewritten in terms of density and volume. Finally, this expression can be rewritten in terms of pressure instead of force by substituting pressure times area for force and dividing the entire expression by area. This results in the final expression for pressure at the bottom of the beaker being equal to the pressure at the top plus density times gravity times height.
Here we have our free body diagram for a cylindrical region in a liquid. The length of the region is delta L, and the difference in height between the upper base and the lower base of the region is delta Z. As you can see, the forces due to pressure are applied along the axis of the cylindrical region. The force due to gravity is pointing straight down in the negative Z direction, and its relative component along the x-axis of the cylindrical region is the specific weight of the fluid times the cross-sectional area of the cylindrical region multiplied by the length of the region multiplied by the sine of the angle alpha. In order to derive the fundamental equation of hydrostatics at hydrostatic equilibrium, the sum of the forces on the region must equal 0. If we define the direction along the axis of the cylindrical region that is up and to the right as positive, dividing all terms of the equation by volume and adding the sum of the pressure forces to both sides of the equation results in the relationship that delta P divided by delta L is equivalent to the specific gravity of the fluid times the sine of the angle alpha. By similar triangles, the angle alpha is equivalent to delta Z over delta L. By multiplying both sides of the equation by delta L and letting delta Z approach 0, the following relationship is that change in pressure with respect to height is equivalent to the negative of the specific gravity of the fluid. This equation is the same one derived using the previous method and also shows that pressure is linearly related to the change in height in a region of fluid.